So we've sketched these two graphs, ln of x, 1 over x, and we found they cross 1. So there is one solution to the equation ln x equals 1 over x, but we can't solve that equation. We haven't got the ability, and that's where numerical methods come in. So sign change questions nearly always say something along the lines of, and I better just check my values rather than working from memory. Yeah. They'll say something along the lines of ln x equals 1 over x has a solution, and often the letter alpha is used to represent that solution. They sometimes use the word root in that context. I'm a little unhappy about that because for me a root is a solution to an equals 0 equation. This isn't an equals 0, but anyway, that's just me being pedantic. And it might say something like, show that alpha is between 1.7 and 1.8. A classic sign change question. Our graph suggests that this solution, so alpha is here, is greater than 1, and they're giving us an even greater steer. This is sign change. There's no mention of sign change, but this is sign change. And so sign change always starts by rewriting the equation as an equals 0 equation. Now we're looking for a root. I'm happy. And we did this at GCSE. There is a value of x where that equals 0. It is unlikely to be a nice round number. It is almost certainly going to be a horrible decimal number. But substitute in 1.7, substitute in 1.8, see if you can use those two results to convince me that the actual solution lies somewhere between those two. I'll give you a second to have a go at that. I've substituted in 1.7 and got a negative answer. Remember, I'm looking for the value of x that makes it equal to 0. Substituted in 1.8, got a positive answer. So the value I'm looking for must be somewhere between 1.7 and 1.8. The sign change from negative to positive indicates that this solution is somewhere between 1.7 and 1.8. The next step is something that you won't have come across at GCSE. Well, you would have done in a different slightly different guise. It would then go on to say, show that alpha equals 1.763 to 3 decimal places. Show that alpha equals 1.763 to 3 decimal places. So they're showing you to demonstrate that the actual answer, it's between 1.7 and 1.8. Actually, to 3 decimal places, it is that. And so this is an error interval question, So the first thing we do in this situation is we say, right, what's the error interval if something has been rounded to 1.763? It's not 1.764, and it's not 1.762. What's the error interval? And hopefully you can see that the error interval for that is so what they expect us to do in this situation is to repeat the sign change, but trying this value and this value. Because if we can show that the root lies somewhere in between those two numbers, then it has to be that to 3, because every number between those two values rounds to 1.763. So in order to do that, we just then try those two more accurate values. And this time I'm going to say sign change indicates that alpha equals 1.63 to 3 decimal places. So again, I'm saying sign change indicates that. So just double check that that works. And if you've used your arrow x approach, then you've still got ln x minus 1 over x on there. So much closer to 0, but one's negative, one's positive. So the root lies somewhere in between here, and every number in between there to three decimal places will be 1.673. So we've shown that that's true. So just very quickly, just practice a couple of those. I've given up the books, haven't I? And then this is a good question. This one you've got to differentiate, and it's the dy by dx equals 0 equation that they're asking you to solve, finding turning points. So yeah, that's quite a nice question, that one. Page 27634 and then page 277, question 10. So differentiating number 10 gives me sine becomes cos, so sine 2x becomes cos 2x multiplied by 2. E to the 4x stays as e to the 4x multiplied by 4 becomes that. We know when we're looking for turning points, we ask when was dy by dx 0. So it's looking like a classic sign change question. We plug in our values. Sign change implies that there is a turning point between those two values, and then to show that it's minus 0.823, we do minus 0.8235 and minus 0.8225. And again, sign change indicates that the stationary point, the turning point, is somewhere between those two. Okay, so sign change, the first step, pretty much as GCSE, with the exception of the little error interval thing. So the second technique, which again we've met at GCSE, is iteration. And iteration is where you take an equation that we're trying to solve and you rearrange it as x equals something to do with x. And then you do the genius thing of saying, right, let's start with a value of x, work out our next value of x, plug that back in to get our second value of x, plug that back in to get our third value of x, and we find that in some situations that converges on the actual solution that we're after. But you may remember that when you rearrange your equation as x equals something to do with x, sometimes it works and sometimes it doesn't work. So let's look at an equation that we can solve already and try and use iteration to solve it, and you know, compare what we know are the answers with what iteration suggests are the answers. Okay? So this is a quadratic. We don't need to use iteration to solve this equation. We don't need to use iteration, but we're going to. I'd like you firstly to rewrite this in 3 different x equals something to do with x ways. I reckon there are 2 obvious ways of doing it and one that's a little bit more subtle. So can you rearrange that equation so it says x equals something to do with x? And then can you also quickly sketch it on your calculator just so we know roughly where the roots are? If you sketch it on your calculator, you'll see where it crosses the x-axis, which are the values that we are looking for. So just do those things for me quickly. Rearrange it as x equals something to do with x, and then have a quick sketch on your calculator just so we know roughly where the solutions that we're looking for are. Go on, Harrison, give me one way I can rearrange it. Can you talk me through your steps?
Add x, and you get x squared minus 1 equals x.
Yep, keep going. Oh, sorry, yes, that's it. So, right, okay, so you've got, yeah, so you've got that, okay? Yeah, brilliant. So that's one way we can rearrange it, yeah? Max, you've got an alternative way of, Max G, got a way of?
You add x and add 1, and then square root that, sorry.
Okay, so we've got good stuff. What you got then, Sean?
Add 1, factor out the x, and then divide by x minus 1.
Yeah, so this grates on me a bit because it breaks the rule, but yeah. So those are three ways that we can rearrange that equation. I'm aware that there's a plus or minus thing going on here, but we'll just assume that's covered by some sort of understanding of the nature of the solution. And of course, hopefully you've sketched it, so we know we've got a root somewhere around -1 and somewhere around 2. Would that be a reasonable suggestion? We've got a negative root and we've got a positive root. Now, this is the thing we do once we've rearranged it as x equals something to do with x. We say, okay, I'm going to use this equation to work out my next value of x using the current value of x. So we're going to say, right, using a particular value of x, I'm going to work out the next value of x, which I'm then going to substitute in. And we do the same in each case. Now that notation tends to scare people off, but it's no need for it to be scary. We're just saying the next value of x is something to do with the current value of x. And in each case we need to start with a particular value, don't we? So, sorry, am I? Is it? Just going back to my graph quickly. I can't remember. Is it closer to -2 than 1, or closer to? No, it's closer to -1. Right. Okay. So, can I suggest that with this rearrangement here, we make -1 our first value? We'll look for the negative root there. And because I'm a bit of a chicken, we'll look for the positive root here, so I'm not going to worry about plus or minus, we'll just worry about, and we'll make our first value 2 in those two, looking for the positive root. We know from the graph that we've just plotted. Now, hopefully, I think I noted that Uplearn does this as well, but if you haven't got to that point in Uplearn, remember you can use the answer button here. So for example, with my example over here, I'm only writing it here so I can put my calculator on the screen. A reminder that you do not need to type this in time and time and time again. What you do is you press, and you don't even use the arrow, you're not using the memory, you're just using the answer function. So I want x0 to be -1, so I just do, sorry, I'm just trying to put the screen up. So I just do -1 equals, and that's then my answer value, and then all I need to do is to type in 1 over answer -1 and keep pressing equals. And what that does is uses -1 in that calculation to get the next value, which is then the answer value, and keeps going. So can I encourage you to try all three of those, to try and find the roots to 2 decimal places? So by basically means stop when you get 2 successive answers which are the same to 2 decimal places. If that's not happening, give up, because we know that you don't always get these iterations to work. Just have a go. See what happens when you try those 3 different iterations. See if you can use it to locate these 2 roots that we're after. We know from our graph And a reminder, we don't use iteration to solve quadratics. We've got proper ways of doing it, but we're just using it as a simple example. So I found that with this rearrangement, I got a root at minus 0.62 after 4 or 5 iterations. And I found with this rearrangement, I got my answer to be 1.62 after a few iterations. And after a few iterations, the one on the left is at 2.5 times 10 to the 14. So this one is not working. And I guess it's fairly obvious if you look at it why it's not working. It's clearly going to get bigger and bigger and bigger. But this is an unhelpful iteration. Now, are we expected to be able to identify iterations that do and don't work? The answer is no. So iteration questions will always start with a show that question. So it would say, show that this equation can be rearranged as this. So that's where they would start, because they clearly don't want to be marking 15 different iterations. So they want everyone to be using the same approach. So you're not expected to be able to look at these and decide which are and which aren't going to work. However, it is a useful skill to be able to explain why it hasn't worked or why it has worked. And this brings in something which is new and not at GCSE, and that is a diagram or a collection of diagrams which we can use to illustrate whether or not an iteration is going to work or not. Those diagrams are sometimes staircase shaped, so they're called staircase diagrams, and sometimes cobweb shaped, so they're called cobweb diagrams. And that's what we're going to look at tomorrow. I can hardly wait. Here we go. Good stuff.